Okay, we're at the end of chapter 2 in the geometry textbook. In this video, we're going to go through the final section, which is on symmetry and transformations. Okay, so we're going to start with line symmetry. What they're talking about here is a figure, like a polygon, for example, being symmetric with respect to a line. What exactly does that mean? Okay, so it says, in the figure below, rectangle ABCD is said to have symmetry with respect to line L because each point to the left of the line of symmetry or axis of symmetry has a corresponding point to the right. For instance, X and Y are corresponding points. All right, so you've got this rectangle ABCD, and they're saying it's symmetric with respect to this line L. And since it's in that case, you can call this line L a line of symmetry or an axis of symmetry. And the reason why it's symmetric is because every single point on the rectangle on one side of the line has what's called a corresponding point on the other side of the line. And what corresponding means is that both points are in the exact same positional location relative to the line on either side. All right, and so to get a more official definition then of symmetry with respect to a line, we need to understand exactly what corresponding points mean, or what does it mean for 2 points to be in the exact same relative position on either side of the line. Okay, and so here's the official definition of symmetry with respect to a line. So a figure has symmetry with respect to a line L if for every point X on the figure, you can pick any point X on one side of the line, there is a second point Y on the figure for which L is the perpendicular bisector of XY. Okay, so this is going to be easier to understand if let's see, is this rectangle symmetric with respect to this line, M? Okay, so if it's going to be symmetric with respect to this line, M, then we have to pick any point on the rectangle, and this analysis can't fail for any point on the rectangle. So we pick, let's do this point here. Okay, we'll call this point X. What they're saying is that this has to have a corresponding point. If you can find one point on the figure that doesn't have a corresponding point with respect to the line you're analyzing, then it's not symmetric with respect to that line. So what the official definition of corresponding means is that you would draw a line that's perpendicular to the line you're analyzing that passes through the point on the figure. So this line here. Okay, now from there, you need to go ahead and continue that line, this perpendicular line, straight through the line of symmetry, the potential line of symmetry, okay, all the way until it gets to the figure. Okay, and then where it gets to the figure, that's point Y. These two line segments need to be congruent. And you can see in this case they're not, so we just found one point that doesn't have a corresponding point. So that means that this figure is not symmetric with respect to line M. Right, so it's going to be perpendicular here, you see? But is it symmetric with respect to line L? Yes, because every single point on this figure, you can find a corresponding point. You can draw a line that's perpendicular to that point or perpendicular to the line of symmetry that passes through that point, and then you can extend that line through the line of symmetry so it's going to be perpendicular then to the line to a point on the other side. And then those two, it's the perpendicular bisector is what they're saying, right? That's what they mean by perpendicular bisector, that there's a line, if you, for any point on the figure, there's a line X, you pick these 2 points X and Y, and you draw a line through those points. That line is a perpendicular bisector of the line of symmetry, the potential line of symmetry. Those 2 points are corresponding, okay? And if it's the case that every single point in the entire figure has a corresponding point, then you can state officially that that line is a line of symmetry or an axis of symmetry for the figure. All right. So now in particular, ABCD of figure 2.38 has horizontal symmetry with respect to line L. Horizontal symmetry. That is, so with respect to this vertical axis, it's saying it has horizontal symmetry. Why is that? Because a vertical axis of symmetry leads to a pairing of corresponding points on a horizontal line. That the symmetry is horizontal, right? It's the corresponding points are horizontally aligned with respect to this vertical axis of symmetry. But then if you have a horizontal axis of symmetry, then that's going to be that leads to a vertical symmetry. Okay, so let's make sure we have the notation clear here. This figure is, we just analyzed how it's symmetric with respect to this line L, and we understand the definition of symmetry with respect to a line. Okay, the nature of the symmetry with respect to this line L is that it's a horizontal symmetry, which indicates that the line of symmetry is vertical. So you can have symmetry with respect to symmetry of a figure with respect to an axis. Okay, but then from there, the way you classify the nature of that symmetry is in the direction that's perpendicular to that axis, because that's how all of the points are corresponding, right? In from the direction of being perpendicular to that axis. That's why the nature of the symmetry is in the direction perpendicular to the axis. All right. So example 1, we come to that same rectangle and think about the horizontal line M and how the figure is symmetric with respect to this horizontal line as well. And therefore, it also has a vertical symmetry. You see, but you can go to every single point on this figure and find a corresponding point with respect to line M on the other side of the line M. So you can make a perpendicular bisector to line M between those 2 points. That's why it's symmetric with respect to line M. Okay, let's look at this example here. Which letters shown below have a line of symmetry? So we've got, let's start with B. So we can see that it's going to have a horizontal line of symmetry. Okay, let's see. D, we can see, is going to have a horizontal line of symmetry. But then that's going to be it for both of these. H is going to have 2 lines of symmetry, horizontal and a vertical. And then G and F are going to have no lines of symmetry. So yeah, that's the case here. But let's be clear, though. Let's really focus on what the official definition of this is, in that you can draw this. I think we all intuitively understand symmetry, right? But it's going to be important to get the precise definition, mathematical definition, clear, and that you cannot find any point on B, on the letter B here. There's no point that's on the letter B here that doesn't have a corresponding point on the other side of this line of symmetry. Corresponding means that if you connect a line segment between those 2 points, that line segment is going to be a perpendicular bisector of the line of symmetry. If you can find just 1 point, so if we're thinking about, okay, does D have symmetry with respect to this line? Well, we can find some points that are corresponding with respect to this line on D. I'm sure we can, right? There's some points that are, but if we can find just 1 point, okay, here's a point on D. Let's draw a line that's perpendicular to this line of interest. Okay, now let's make it the perpendicular bisector. So equidistant and straight through, we know that means it's perpendicular, equidistant in the other direction. Well, look, it's not on, the other point is not on D. So we found just 1 point that doesn't have a corresponding point, so it's not, that figure is not symmetric about that line. That's probably a better way to analyze for symmetry, a figure for symmetry about a line. You just pick different points and go ahead and draw the perpendicular bisector, and then see if, okay, there's the perpendicular bisector, does the other side land on the figure? If it doesn't, then you found a point on the figure that doesn't have a corresponding point, right? It looks like here we could do that. So there's the perpendicular bisector, or the perpendicular distance to the line. Now let's draw the perpendicular bisector, okay, that looks to have a corresponding point. But again, we just did a point where that it didn't work. There you go. In Chapter 4, we will discover formal definitions of the types of quadrilaterals known as the parallelogram, square, rectangle, kite, rhombus, and rectangle. They state rectangle twice for some reason. Some of these are included in examples 3 and 5. Okay. Which geometric figures below have at least one line of symmetry, and which have more than one line of symmetry? So what we're going to see is that a figure can have multiple lines of symmetry, potentially. Or it could just have one, or it could have none. So, all right, this here they give an isosceles triangle, so it's just two of the sides are congruent, but not the third side. And so, in that case, we're going to have at least one line of symmetry right down the center here, this vertical line. But you could think about if it was equilateral, then we'd have at least two more. But since it's not equilateral, you can think about how there's just going to be one here with the two congruent sides on either side of the line of symmetry. Okay, now a square, you'll have, okay, well, one down a vertical and horizontal line of symmetry for sure. But then even the diagonals, right? Okay, now this quadrilateral here, it's hard to tell for sure. It looks like maybe there could be one, but if it's hard to tell, then you'd have to go through the official definition and like systematically check. But maybe, maybe here, maybe. Okay, now here's a regular pentagon. Well, we've got one down the middle for sure, vertically. And what we would find is that you would have, actually, there's more lines of symmetry for a regular pentagon than there are for a square, which is very interesting. So you'd have one here, and then there's going to be, it's like this. So pretty cool. And yeah, if we look at the answers here, yeah, there's 5 lines of symmetry for a regular pentagon, 4 for a square, 1 for an isosceles triangle, and then this had none. Okay, so that's line symmetry. Now we want to think about point symmetry, a figure being symmetric with respect to a point. In figure 2.41, rectangle ABCD is also said to have symmetry with respect to a point. As shown, point P is determined by the intersection of the diagonals of the rectangle. So, yeah, if you draw the diagonals where they intersect is the point P that this figure is symmetric about. It's like the center point. Okay, so we can think about it's going to be a similar idea with respect to symmetry about a point, as far as you're going to have corresponding, every single point on the figure is going to have a corresponding point with respect to point P. But we just need to understand what exactly it means for 2 points to be corresponding with respect to not a line in this case or an axis, but a point. All right, so a figure has symmetry with respect to point P if for every point M on the figure, there is a second point N on the figure for which point P is the midpoint of segment MN. Okay, so in this case, there's no perpendicularity associated with point symmetry. This actually is a little bit simpler than line symmetry. It's just that you pick any point on the figure, any point. Okay, and if that point, for that point to have this corresponding second point with respect to point P, then there has to be another point on the figure somewhere to where if you connect a line between the initial point X here and that point that goes through point P, then point P is going to be the midpoint of that line segment. Then those 2 points are like, you could say, corresponding with respect to point P. And every single point on the figure, every single point needs to have a corresponding point with respect to point P. Then you have symmetry with respect to point P of that figure. If you find just one point that doesn't have this partner point with respect to a certain point of potential point of symmetry, then it's not symmetric with respect to that point. That's the idea. So these need to be congruent. These two, it needs to be, the P needs to be the midpoint of X, Y. Okay. So on the basis of this definition, each point on the rectangle above has a corresponding point that is the same distance from P, but which lies in the opposite direction from P. In figure 2.41b, M and N are a pair of corresponding points. Even though a figure may have multiple lines of symmetry, a figure can have only one point of symmetry. So yeah, this is important here. So it says, even though a figure could have multiple lines of symmetry, we saw that was the case. You have the pentagon has 5 lines of symmetry. A figure, however, can only have one point of symmetry. You can't have a figure can't have multiple points of symmetry. Thus, the point of symmetry when one exists, or maybe, so a figure is going to either have one point of symmetry or no points of symmetry. But so in that case, though, if it does have a point of symmetry, that point is unique. Okay. Which letters have a point of symmetry? So, okay, M. Let's see, M. All right, so we're just thinking about, is there some point, obviously this point's going to be kind of in the center of the figure. It has to be. So somewhere like around here, I guess. Yeah, this looks like the answer is going to be no here, because you can't. Okay, so I mean, maybe that's a yes. These 2 points are corresponding, okay. But then, like, okay, well, here you go. No, obviously no. This point doesn't have a corresponding point with respect to this potential point of symmetry. But again, you can think about there's no way you can have a point of symmetry for a figure that's not like around the central area of the figure. How could then you're going to fail the test every time, the point symmetry test? So we're going to have to be somewhere. The point of symmetry is going to have to be somewhere around here. Has to be. And you could just see this would fail every time. This region would fail every time, because you're going to have to connect these points. There's a straight line that goes through that point to some other point over here that doesn't exist. So no, M's not going to have a point of symmetry. What about N? Yeah, this looks good, because you're going to have a point, right in the middle here. And yeah, you could pick any point, and it's going to have a corresponding point on the other side. Right? Passes through that midpoint or passes through that central point, and the central point is the midpoint of the line segment connecting the 2 points. So yes, point N has a point of symmetry. What about point P? Or no, what about the letter P? So no, because you can, again, it's going to have to be kind of in the center here, like around here. Well, look, I mean, there's no way this isn't going to work, right? Okay, what about S? Yeah, that looks good. Yeah. And then X looks good as well. Definitely, X looks very symmetric in a lot of ways. Lines of symmetry, points of a point of symmetry. So now it's interesting to think about. It makes you kind of wonder. Okay, if a figure has a point of symmetry, then it must have an axis of at least one axis of symmetry, right? Well, I think that makes me think about algebra, and that you can have a graph that's symmetric with respect to the origin, which the origin is a point, but it doesn't have any symmetry about the vertical and horizontal axes. Like that would be a graph like this, a shape like this. Well, this is symmetric with respect to this point, right? It passes that straight line, right? but this doesn't have any symmetry with respect to an axis, right? So I've just answered that question. No, not necessarily. You don't, just because you have a symmetry about a point doesn't mean that doesn't imply that there has to be symmetry about an axis. But now the reverse is an interesting question though as well. If you've got at least one axis of symmetry, does that mean that there must be a point of symmetry for that figure? And we can quickly think about how the answer to that question is going to be no as well. Here's a parabola which is symmetric about this vertical axis. You can draw, every point's going to have a corresponding point. But clearly this doesn't have a point symmetry. If we, let's make an actual figure here. Let's say this is the figure. So a central point would be somewhere, I guess, around here maybe. So the point of symmetry would have to be around here. Well, no way. I mean, here's this line is midway, passes through this potential point of symmetry, and it's equidistant on both sides. Well, this isn't on the even close to being back on the figure. Okay. Which geometric figures have point symmetry, have a point of symmetry? So looks like here, yes, right in the middle there. Here definitely. Here definitely. Here definitely. What about here? Again, it's going to have to be in the center. And, yeah, it looks like yes. So all of these would be yes, I would say. The regular pentagon, no. What? Or no, okay, this, they're saying no. Yeah, I guess so. Right, because, I messed that up. Because here, the answer is going to be no. Interesting. Yeah, exactly. This is, you can see, this is going to be a little bit longer than this, so no. And I guess that would be the case. You can kind of see that here as well. Well, those look close. No, this is a little bit longer than this. These aren't congruent, so no. But all the other ones are a yes. Okay, now before we move on to this next section on transformations, let's think about how everything we just learned about line and point symmetry would extend to 3D space. So we're not going to do anything official here. We're just going to use our intuition to think about how these concepts extend into 3D space. And it's going to be a very intuitive extension, you'll see. So, okay, if we had, let's say we had some rectangular prism type object. Maybe this is a box, or it's, even it's solid, fully solid, doesn't really matter. Okay, the idea of is this box symmetrical with respect to any line is going to be the exact same concept as what we just learned in 2D, but in 3D. So if this box or solid is symmetrical with respect to, say, this line here, then you can pick any point. Let's say it's a solid rectangular prism. You can pick any point anywhere in the solid, okay, and it's going to have a corresponding point on like the other side of the line. Okay, but what does corresponding mean in this sense? Same exact idea as what we learned in 2D. It's going to be you construct a line that's perpendicular, that goes through the point you picked, and it's perpendicular to the potential line of symmetry. That's going to be a unique line. Okay, but then you just extend that all the way through, equidistant on the other side, and that's the perpendicular bisector to the line. That the point on the other side needs to be on the solid for any point you could possibly pick anywhere. Then it's symmetrical. Now, this just gets a little more challenging because you have to understand the mathematics of lines that aren't, in lines in 3D space, right? And understand how would you mathematically represent a line that's not oriented necessarily parallel to the main axes, that's perpendicular to some randomly oriented line as well. Well, we learned the mathematics, the algebra of lines in 3D space, etc., and how to find perpendicular directions, whatnot. And that's what we do in at the beginning of Calculus 3, and that's what you need to understand vectors to construct perpendicular directions and whatnot. But the concept is exactly the same, though. It's just this: you have to have for all points on the solid. Again, for all points on the solid, if you're seeing if that solid is symmetrical with respect to a line, for all points, then you have to be able to have another point on like the opposite side of the line that corresponds to that point you picked, in the sense that you construct a perpendicular bisector going through those 2 points that's perpendicular to the line of interest, and both of those points are on the solid. Okay, now a point of symmetry is also the exact same idea. You're going to pick any point in the solid, and then that point needs to have a corresponding point with respect to the potential point of symmetry, to where there's some other point, like you draw a line that goes through the point you picked to the point of symmetry, and then just keep going through equidistant. Okay, and that whenever the other point has to be on the solid. If it's off the solid, then that's not, if you find just one point to where you go equidistant through the point and you're not on the solid, but you started on the solid, then that's not going to be that point is not a point of symmetry. Okay, but now in 3D though, we also have the option of symmetry about a plane, which we didn't. This wasn't an option in 2D, right? Okay, but we can use our intuition to understand what this is going to mean in 3D. So if this rectangular prism here is symmetric with respect to this plane, then it's going to be the same idea. You have to be able to pick any point on the solid, and there needs to be a corresponding point on like the opposite side of the plane. Okay, but the question is, what does corresponding mean here? Well, okay, that's going to be the plane is going to be a perpendicular bisector. You're going to connect the point you picked to the plane with a line that's perpendicular to the plane, and then just continue that line through the same distance up to the opposite side, and then that point on the opposite side needs to be on the solid. That's the idea of corresponding points with respect to a plane. And that's it. And there you go. That just gives you a sense for symmetry in 3D space, but we didn't go through anything official here. Okay, so now we want to talk about transformations of figures. What they're talking about here is that we could start with a figure, like any kind of polygon or triangle, or even a 3D solid body, like this, for example. Okay, and starting here, we could transform this triangle, which means we could shift it up, down, left, or right, or into or out of the page, whatever, flip it, stretch it, shrink it, whatever. Okay, so we could move it, rotate it, scale it up or down, stretch it in any direction. Okay, and so with that, when we study transformations, we're just wanting to be able to break down how exactly this figure here was transformed from state 1 to state 2. That's what transformations is all about. What linear movement, rotation, flipping, stretching, shrinking, and in what directions caused this figure to go from this state to this state? What was the transformation, the exact transformation? Okay, now in this section, we're only going to focus on one type of transformation. And these are called rigid body transformations. And what a rigid body transformation is, it's a transformation to where you're only changing the orientation or position of the figure, to where the two figures before and after the transformation are congruent. And so what did we talk about the meaning of congruence is between figures? Well, okay, we could take this triangle and we could do anything we want to it except for changing its size or like the relative position of its features. So we don't want to stretch it, shrink it, scale it, anything like that. But we can translate it. We can rotate it. We can flip it. We could rotate it into or out of the page. You could do this, in any way you want in 3D space, any kind of reorientation. Okay, all of these types of transformations, the shifting it, flipping it, rotating it, are called rigid body transformations, and that's what we're going to study in this section, these types of transformations. But you can see with these types of transformations that we have two congruent triangles here, because all of the corresponding side lengths are still exactly the same. All the corresponding angles are still exactly the same. They haven't changed. That's what makes the two triangles congruent. So that's the key feature of a rigid body transformation. After a rigid body transformation, the two figures are still congruent. Okay, and so with that, though, what's going to be important is, and really this is important with any kind of transformation, not just rigid body, but after a transformation, it's important to be able to identify the features that correspond to one another. So what are between these two figures here, what are the corresponding vertices? So if we started with triangle ABC, okay, and we transformed to triangle XYZ, okay, well, which vertice is X, Y, and Z? That's important to be able to identify that correctly, and not just for rigid body transformations, any kind of transformation. So, okay, so X corresponds to A, Y to B, Z to C. So let's see, we've got this longest leg here, BC, and here's the longest leg. So one of these vertices is Y and one is Z, but which is which? So, okay, we can take, let's see, let's unflip it. So the leg on the left side matches up with AB. So, okay, in that case, then this is going to be Y, this is going to be Z, and this is going to be X. And there you go. All right, let's start by understanding the nature behind a slide or a translation. Okay, so you take the figure and you're just moving it anywhere in 3D space. Okay, so what's going on here is, like mathematically, geometrically, is that, so, okay, if this is A, B, C, and this is X, Y, Z. Okay, so let's say we're saying that triangle A, B, C underwent this pure shift or pure translation, resulting in triangle X, Y, Z. So with this, we can see point A corresponds to point X, point B to point Y, C to Z. Okay, what this means is that, so for any transformation, no matter what the transformation is, you'll always be able to start the analysis of the transformation by taking two corresponding points, like, okay, A and X, and specifying what is the distance and direction that point transformed, right? It doesn't matter what you do. You could stretch it, shrink it, whatever. Every corresponding point moved some distance in some direction, right? Okay, but with a pure translation, a pure shift, all of the corresponding points moved in 3D space the exact same distance in the exact same direction. So like this is a vector, right? This AX is a vector. this is going to be that exact same vector, that exact same distance, and that exact same direction. This is going to be exactly the same. This in the middle is going to be the exact same vector. For any other kind of transformation, even other rigid body transformations that we're about to study, like flipping and rotating, this isn't going to be the case. Again, yes, it is the case that you can compare corresponding points, and they're all going to have some sort of a shift like this, some distance in 3D space and direction, right? But they're not necessarily all going to be it's going to be different shifting amounts, different shifting directions. But with just a pure shift, a slide, a translation, the movement of points on the original figure in terms of the direction and distance of movement in 3D space are exactly the same for all points on the entire figure. Okay, but you can see though when it comes to a slide or a shift, a translation, the before and after figures are congruent, right? This side is still the same length as this side. These two sides are the same length. These two sides are the same length. The corresponding angles are the same. They're congruent figures. That's going to be the case for any rigid body transformation. Okay, so now they work a couple of examples here, but we'll work plenty of examples in the upcoming videos. Let's move on to the next rigid body transformation type, the reflection. A reflection is also known as a flip or a mirroring. So what we're doing is, with this type of transformation, we're taking a figure and we're going to reflect it about, let's start with a line. We can reflect about a plane, a line, or even a point, but let's start with a line here. So we can think about the idea of transforming a figure by reflecting it about a line, or flipping it about a line, or mirroring it about a line. And all that means is that you're going to have so if we look here, we're going to have the figure before the transformation and the figure after the transformation. But when you compare the before and after figures, they're going to be symmetric with respect to that line or the plane, if we're thinking about in 3D or that plane. That's the idea. Okay, so for example, here's this triangle. I can tell this sketching software to flip the layer vertically, and all that did was so the layer is the whole layer that triangle is in. It was drawn in is something like this. And so when it says flipping it vertically, the layer vertically, it's flipping it about the horizontal center line. So the original triangle and the transformed triangle are symmetric with respect to this center line here. Okay, now, but in a similar way to how with line symmetry, there was the idea of you could have symmetry about a vertical line, but you could describe that symmetry as being a horizontal symmetry. It's the same idea in that here we flipped about a horizontal line, but it was a vertical flip, right? Here we flipped about a vertical line, but you can also describe that as a horizontal reflection, because the reflection is horizontal, right? Now, but again, it's also important to be able to specify make sure you correctly understand what points correspond to which. So in this case here, you had triangle M in P was transformed via a flip or a reflection about this vertical line here into what triangle? Into triangle GHK, right? M corresponds to G, N corresponds to H, P corresponds to K. But what you can notice, though, is that this is different from this is still a rigid body transformation, right? These two triangles are congruent. These side lengths are equal, these side lengths are equal, these side lengths are equal, and then the corresponding angles are equal, right? But if we think about the vector that connects these 2 points, right? So via the transformation, M moved this distance in this direction to G. Okay, now, but look at P to K. That's 2 different distances, same direction, but it's 2 different distances. It's a different vector. But remember, with a translation, a pure shift, this displacement vector for all corresponding points was exactly the same. Here it's not, but it's still a rigid body transformation, right? The figures are still congruent after the transformation. Okay, now they also note that we can flip about any line or reflect about any line. It doesn't have to be a vertical or horizontal line, right? It's just, you can flip anything about any line or plane, whatever, oriented in any way. Okay, now they work some more examples, but again, we're going to work plenty of examples to make sure you have a full understanding of this in the upcoming videos. Let's move on to the last type of rigid body transformation. That's a rotation. Okay, in a rotation, every point of the given figure leads to a point by rotation about a given point through a prescribed angle measure. Okay, so let's come to the next page. So here the figure is ray AB, and it's transformed with a rotation, which means that every single point on ray AB, every single point, rotated 30 degrees about point A. That's the idea. Okay, so for example, let's take this triangle here, and we're going to rotate it about this point. Okay? What you can see is that every single point on the triangle, if you compare corresponding points before and after, they're all going to go through the exact same amount of rotation about that point. So let's see. There we go. So if we draw a line here, those are corresponding points, right? We just, okay, let's see. We just transformed, let's say, triangle A, B, C to triangle X, Y, Z. So triangle A, B, C was transformed to triangle X, Y, Z by a pure rotation. Okay, you could draw, what this means is that you could analyze the angle change between corresponding points on the untransformed and transformed figure, and it's going to be the exact same angle change. Even, it doesn't have to be vertices, even with the center point. It's going to be that exact same angle change, right? So all these rays, if we look here, you've got these two segments here. Well, that defines a plane, and there's an angle here. Okay, you could do this anywhere, as long as the points are corresponding. There's another plane, there's an angle here. It's going to be the exact same angle. If this is a pure rotation, those angles are going to be the same. And you could think about how this applies in 3D. It's just whatever the point is, you just connect a line segment between corresponding points on the transformed and untransformed figure to that point of rotation, and you're going to get these two line segments that defines this unique plane to where that angle between the two line segments is going to be. All those angles for the entire figure are going to be the same, as long as you've connected line segments between corresponding points and the point of rotation. Okay, now if you're still a little bit confused, let's work some example problems, and that'll clear up any confusion and help to cement all this information for you.